The idea of the inverse of a 2 by 2 matrix is somewhat esoteric at the moment. Where does this inverse come from? And it turns out there's a lot of really cool intuition behind the computation of an inverse. So let's just take a moment and think about this general system of two linear equations, this 2 by 2 system. A times x plus b times y equals f. C times x plus d times y equals g, and a, b, c, d, f, and g are just some constants, just some real numbers. So to get a little bit of a sense of intuition, let's go over to Desmos and simulate some of these values. So to better understand what some of these constants do, I just entered ax plus by equals f and cx plus dy equals g. And we can see that the red line right now is for a equals 1, b equals 1, f equals 1. Now I can change these and see what effect that has. And I see that changing a appears to affect the slope of the line. So at least so far we can conclude that the value of a is going to change or have an influence on the slope of that line, ax plus by equals f. If I do the same thing for b, I notice that that too changes the slope. Perhaps in a different way, but it does change the slope nonetheless. And the value of f, well, it looks like it's a right-left shift, but it's actually shifting the line up and down. It's affecting the vertical intercept. So that value of f is actually not changing the slope. And therefore, if it's not changing the slope, as long as the slope of the two lines are different, how far up or down you shift one of the lines is not going to influence the fact that there would be an intersection point if those lines have different slopes. Now I can do the same thing over here, and we see that that again changes the value of the slope, and d changes the value of the slope as well. And g, what it does is it again creates that vertical shift. So provided that the slopes aren't the same, changing the values of f and g should not change the fact that there will be a distinct solution. So let's come back over here and do a little bit of analysis. So we know that a, b, c, and d are involved somehow in the slopes of these lines. And let's see exactly how that is. If I take the first equation here and I solve that for y, I'll have by equals negative ax plus f. And dividing both sides by b, I get y equals negative a over b times x plus f over b. Okay, so we can see that a and b, they actually do indeed affect the slope. They were also changing the vertical intercept, if you notice how we were rotating those lines. But most importantly, they affect the slope. If I do the same thing for the second equation, and I solve for y, dy equals negative cx plus g, and I divide both sides by d to get it into the slope-intercept form, I have y equals negative c over d times x plus g over d. And so once again, I can see that the values of c and d are influencing the slope. Now, the one situation for a system of two equations and two variables where we can guarantee that the two lines will intersect is if they have different slopes. So if two lines have different slopes in two dimensions, they will always intersect at one point. So two lines in R2 with different slopes will always intersect once. Now there are the fringe cases where, okay, what if the slope is undefined, if it's a vertical line? And yes, that can happen, but let's just go ahead and focus on the typical cases here for now. Okay, so what does this mean? So in translation, in mathematical terms, the slope of the first line is negative a over b. The slope of the second line is negative c over d, and we're saying if they're different, so in other words, if negative a over b is not the same as or not equal to negative c over d. Well, if that's the case, you could certainly agree that if I multiply both sides by a -1, they're still not going to be equal to each other. So A over B is not equal to C over D, which then furthermore translates into the statement that if I multiply both sides by D and by B, I get AD is not equal to BC. And if I do a little bit more rearranging and subtract BC from both sides, I see that AD minus BC is not equal to 0. Now that's interesting because in the computation for matrix A, we recall that, pick a different color here, we recall that if A has components A, B, C, and D, then A inverse will equal 1 over AD minus BC. And you notice that this and the denominator are exactly the same. And we can see why it's important that AD minus BC is not equal to 0, because if it is, the inverse is not going to exist. So this AD minus BC actually turns out to be something called the determinant of this matrix, which we'll get into a little bit later. And then, of course, there's this weird, these two components get switched, the A and the D, and then the C and the B stay in their place, but they get negated. Okay, so we can kind of see that what this has to deal with is the fact that the slopes are different as long as AD minus BC is not equal to 0. And as long as the slopes are different, that means the two lines will intersect, and if the two lines intersect at exactly 1 point, we know that that means that A inverse exists. Now what we still don't know is kind of where these components come from. And the best way, or one of the ways to arrive at that, is to try to reduce our system using Gaussian elimination. Okay, so our system was AX plus BY equals F, CX plus DY equals G. So AX plus BY equals F, CX plus DY equals G, and we were trying to solve this system. And while we'll learn a more efficient way to find the inverse, let's say we started applying row reduction operations to this. So here's where working with Gaussian elimination actually comes in handy sometimes whenever you're trying to do something symbolic. So to get this into a 1, what I would first do is take 1 over A times row 1. And what that will do is that will 1 over A times A is 1, 1 over A times B is B over A, and 1 over A times F is F over A. Okay, so then we have C, D, G down here. Now the next thing I'll go ahead and do is I will use the 1 to cancel out the C. So that means I'm going to take negative C times row 1, and I'm going to add it to row 2. So negative C times 1 is negative C, plus C is 0. Negative C times B over A is negative CB over A added to D. So negative CB over A added to D. So all I've done there is just take a negative C times this value, and I've added it to this value. I can't really do much more than that because I don't know what D is, so I can just leave it as that expression. And negative C times F over A is negative CF over A plus G. Gives me negative CF over A plus G. And then my first row is just 1, B over A, F over A, and we can continue going on in this fashion. So to save some of the details here and some of the messy algebraic details that it would take us to eliminate this, what we end up with is the following reduced row echelon form. And you can see that in this solution we're saying that X is going to equal df minus bg over AD minus BC. And there's that AD minus BC again. So if AD is equal to BC, that means the two slopes are the same. And if the two slopes are the same, then there's not going to be a unique solution. There's either going to be 0 or infinitely many. And according to this, this says that y is equal to CF minus AG over BC minus AD, and that's the negative of AD minus BC, but still AD and BC can't be equal, because if their slopes are the same, I'm not going to get a real solution here. Now what I'll go ahead and do is I will write this as a equality of vectors. And what I'm going to do is I want to see that what this really is that this is my A inverse times my B matrix. So what I'm going to do first is I'm going to split this up into two pieces. I'm going to split this up into DF over AD minus BC. And then I'm going to create another vector here that's just going to take on that residual, that negative BG over AD minus BC. So I'm splitting that fraction up into two pieces. And down at the bottom, I'm going to do the same thing, except I will have CF. Now, you know what? Since BC minus AD, since that's really just the negative of AD minus BC, what I'll do is write AD minus BC and pull out a negative sign. And I'll do the same thing over here. I'll have negative AG over negative AD minus BC, so that will just be positive AG over AD minus BC. And what I'll go ahead and do next is I can see that all four of these pieces have an 1 over AD minus BC in it. So I'll factor out a 1 over AD minus BC, and that will leave me with just DF here and with negative CF here. And, oh, you know what? I suppose I could also, no, I won't do that quite yet. And I will write this as, well, you know what? I guess we could also write 1 over AD minus BC here times negative BG and AG here. And we're getting closer to seeing that this is really the coefficient corresponding to that determinant. So let me actually go ahead and write it out like this. I'll state that this can further be written as F over AD minus BC times the D negative C vector plus G over AD minus BC times the negative BA vector. And what I know by vector multiplication is that this could actually be written as, the matrix D negative B negative C and A. And oh, hey, guess what? That's part of this inverse. D negative B negative C positive A. The A and the D have been switched. The C and the B stay in the same place, but they've been negated. And then the vector here will be F over AD minus BC. I'm kind of doing some extra steps here. I could have made this a little bit faster, but. And so what I'll go ahead and do next is I see that I can factor out 1 over AD minus BC here. So I'll pull that out front. And then I have the D negative B negative C A matrix. And then what's left inside of here is just F and G. Now here we are. We're at the end. We just said that all the way down, this is what the XY vector is equal to. And let's try to make some connections now. So this is what we call vector X. This right here is what we call vector B. And so that must mean that all of this right here is the A inverse matrix. And so there's kind of our algebraic roundabout way of seeing this. And that also we can make a connection to the idea of slopes, that these are linear functions. And in 3 dimensions, a similar analogy applies. But when we're thinking about 3-dimensional functions, we don't just have one slope like we have with a line. We have this slope, but we also have this slope. So there are kind of 2 different tilts. And so as a result, in the idea of that the slopes have have to or can't match up in certain ways. It just gets a little bit more complex to think about, but it's an analogous idea to what we're doing here in 2 dimensions.